Hello everyone, welcome to Lesson 8 of Pre-Algebra. In our last lesson, we started a new unit on number theory, and we introduced the concept of prime numbers and prime factorization. So in our lesson today, we're going to continue into part 2 of number theory, and we're going to learn about greatest common factor. Okay, let's start. So previously, if you recall, we learned about prime factors. Then what is a greatest common factor? So greatest common factor of a set of numbers is the largest factor that all the numbers share. So in another word, if I have a set of integers, then that largest number that is a factor of each integer is the greatest common factor. So greatest common factor is also denoted in short as GCF. It's also called the greatest common divisor, GCD. Let's walk through a few examples to see how to find the GCF on a set of integers. In this example, it's asking find the greatest common factor of the following number sets. Let's look at our first set, 108 and 45. So let's first write out the prime factors for each number. So we start with 108. We're going to divide this number by 3, and that leaves us with 36. Then we divide it by 3 again, that's 12. Then we're going to divide by 3 again, that leaves us with a 4. And 4 is equal to 2 times 2. Now let's look at 45. So 45 divided by 3 is 15. 15 is 3 multiplied by 5. Okay. So 108 written in terms of prime factors equals to 3 times 3 times 3 times 2 times 2. And 45 is equal to 3 times 3 times 5. Okay? So now let's see. What are some of the prime numbers that are common to both? We have a 3 here that's common to both. And we have a 3 here that's also common to both. And that's it. So our greatest common factor for these two numbers is 3 times 3, which equals to 9. And let's check our answer to see if it makes sense or not. So is 9 a factor of 45? Yes, it is. 6 times 9 is equal to 45. Is 9 a factor of 108? It also is. 12 times 9 is equal to 108. Okay. Now let's move on to this problem. 360 and 48. So again, we're going to do a prime factorization on 360. So if we divide that number by 3, it's 120. Divided by 3 again is 40. Then we divide it by 2 is 20. Divided by 2 again is 10. And divided by 2 again left us with a 5. Let's look at 48. So 48 divided by 3 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 left us with a 2. Okay. So 360 is equal to 3 times 3 times 2 times 2 times 2 times 5. And 48 equals to 3 times 2 times 2 times 2 times 2. Okay. Now let's find the common factors in both numbers. So we have a 3 here. We have 2 that's common to both, another 2 that's common to both, and one more 2 that's common to both. And that's it. So the greatest common factor for these two numbers is 3 times 2 times 2 times 2. And that equals to 24. And let's again check our answer. So is 24 a factor of 48? Yes, it is. 2 times 24 is equal to 48. Is 24 a factor of 360? Yes, it is. 24 times 15 equals to 360. Okay, so that's how you find greatest common factors for a set of integers. Now, what happens if we have two integers where they have no common factors other than 1 between them? If that is the case, then these two integers are called relatively prime to each other. For example, We have two numbers, 108 and 35. 108 can be factored out as 2 times 2 times 3 times 3 times 3. 35 can be factored out as 5 times 7. So if you look amongst all the factors, there's not a single one that's common to both numbers. So in this case, these two numbers have no common factors, so they're relatively prime to each other. Now let's look at another example, 17 and 13. So both of these numbers are prime numbers. They also do not have a common factor other than 1. So these two are also relatively prime to each other. Let's take a look at Venn diagrams. So Venn diagram is a powerful tool that's used in helping us solve number theory problems such as finding the greatest common factors. It's basically an illustration that uses circles to describe the relationship among items. Okay? So items are grouped into overlapping circles. So in here we have items that are grouped into two circles, group A and group B. Now there are some of the items that are common to both, okay, that appears in the overlapping section of both circles. And there are some items that's only unique to A, which they do not appear in B. And there are some items that are unique to B, which they do not appear in A. Okay? So Venn diagram is basically there to visualize the relationship of these items with respect to the group or groups. So next, let's walk through a few examples that uses Venn diagrams to help us find GCFs. In this example, find the greatest common factor of 84 and 140. So first, we need to find the prime factors of each number. Let's start with 84. 84, we factor out a 2, we're left with 42. Factoring out another 2, we're left with 21. And 21 is 3 multiplied by 7. Now let's look at 140. Factor out a 2 leaves us with 70. Factoring out another 2, we're left with 35. 35 is 5 multiplied by 7. So 84 is equal to 2 times 2 times 3 times 7. And 140 is equal to 2 times 2 times 5 times 7. Okay. Now let's use Venn diagrams to illustrate all these prime factors. Let's first have one circle that represents the number 84. So all the prime factors of 84 will go under this circle. Now let's have another circle that represents the number 140. So similarly, all the prime factors of 140 will go under this circle. There's an overlapping region between these two circles, and that means that all the factors that are common in both numbers will be appearing here. Okay? So let's take a look. First, we have number 2. That is a factor common to both. So the 2 will be here. Next, we have another 2 that's also common to both. So this 2 will also be sitting here. Then you can see we have a 7 that's common to both. The 7 will be also in the overlapping region. Then we're left with 3 and 5. Okay? So 3 is unique only to 84. So 3 will be sitting here. It cannot be in the overlapping region because although it is part of 84, but it is not part of 140. So it will be here. Similarly, for number 5, it will be in this region because it's only unique to 140. Right? So you can see the overlapping region has 2 times 2 times 7, and that is our greatest common factor, which is 28. Next, in this example, it's asking to find the greatest common factor of 36, 48, and 90. So now we're dealing with 3 numbers. And our first step, as before, is to find the prime factors of each number. So for 36, we have 2 times 2 times 3 times 3. And for 48, that equals 2. 2 times 2 times 2 times 2 times 3. And for 90, that equals 2. 2 times 3 times 3 times 5. So this is our set of prime factors that belongs to all three numbers. And we're going to use Venn diagrams. We're going to draw 3 circles. Each circle represents one number. So our first circle is circle for number 36. And we have another circle that represents the number 48. And finally, we have one more circle on the top that represents the number 90. And we're going to see how all of these prime factors maps into their relative location on the Venn diagram. Okay. So first, let's look at prime factors that are common to all three numbers. So we have a 2 here that is common to all three numbers. And if we put that 2 on the Venn diagram, that means it must be in the location where all three of them overlaps. And that's the center region right here. So the 2 will be sitting here. Okay. And we again have another number, 3, that is common to all three numbers. And similarly, this 3 is going to be in the same location on the Venn diagram. Okay. So these are the 2 prime factors that are common to all three numbers. And next, we're going to look at prime factors that are common to 2 numbers. For example, this 2 right here. This 2 is common to 36 and 48. So for the circle 36 and for the circle 48, the common area is right here. Okay? And this 2 will be sitting right here. Now this line belongs to the circle 90. The 2 cannot be on this side of the line because it is not a prime factor that is left over in 90. Okay. Now let's take a look at this 3. This 3 right here is common to number 36 and 90. So we find the circle 36 and the circle 90, and their overlapping region is right here. Okay. So the 3 will be sitting right here. This line is part of the circle 48. 3 cannot be on the other side of the line for the similar region because 3 is no longer a leftover prime factor in 48. So next, we're left with prime factors that are unique to only one number. Okay. So for this 2 and this 2, it's only unique to 48. So it sits in this region here. And for this 5, it's only unique to number 90. So the 5 will be sitting right here. So if you look at this Venn diagram, where all 3 of these circles overlap is right here. And that is the greatest common factor area. Okay? So the greatest common factor for all 3 numbers is 2 times 3, which equals to 6. Next, let's look at a few practice problems. In this problem, it's asking, in a candy store, every candy bag has the same number of candies. Amy bought a total of 70 candies, and Betty bought a total of 42 candies. What is the smallest number of bags Amy and Betty could have got? Now, if you look at this problem and think about it, the more candies that can be placed into one bag, the smaller the number of bags is needed. So if we're to find the smallest number of bags that Amy and Betty could have, then we need to find out what is the largest number of candies that can go into one bag. So if we let C represent the number of candies in one bag, so the number of candies per bag, and we let M represent the number of bags of candies Amy has. So the number of bags for Amy. And we let N represent the number of bags of candies Betty has. So for Betty. Then we can write out 2 math expressions. We start with 70, which is the total number of candies Amy has. This is equivalent of the number of bags she has multiplied by the number of candies per bag. And we have 42, which is the total number of candies Betty has. This is equivalent of the number of bags she has multiplied by the number of candies per bag. So we want to make the number of bags as small as possible. That means to make the m and n as small as possible. So this will make the c as large as possible. Now c here is a common factor to both 70 and 42. So to make c as large as possible, that means we're looking for the greatest common factor for both of these numbers. Okay, so let's find that. So 70 is equal to 7 multiplied by 2 multiplied by 5. And 42 equals to 7 multiplied by 2 multiplied by 3. So you can probably already see here the greatest common factor is 7 multiplied by 2, which is 14. So this 14 here is C, and that is the largest number of candies per bag. Okay, so that means M is equal to 70 divided by C, which is 14. And that gives 5 bags for Amy. And N is equal to 42 divided by C, which is 14. That equals to 3 bags for Betty. Okay. So these two numbers are the smallest number of bags for Amy and Betty. Let's look at our last practice example. The number 6,545 can be written as a product of a pair of positive two-digit integers. What are these two integers? So in our first step, we're going to find all the prime factors of 6,545. So we start with 6,545. This number ends in 5, so we know it's divisible by 5. Okay, so if we divide this number by 5, we're left with 1309. Okay, now if you take a look at this number, the sum of its even digits is 12. The sum of its odd digits is 1. And the difference between the two is 11. 11 is divisible by 11, so that makes this number divisible by 11. Okay, so we're going to divide this number by 11, and that leaves us with 119. Okay. Now, if you look at 119, this number is not divisible by 2, nor 3, nor 5, nor 11. And if we try out 7, luckily 7 is also a prime factor, and that results in a 17. 17 itself is a prime number, so that ends the prime factorization. Okay, so the number of prime factors we have is 4, and they are 5, 11, 7, and 17. And we're going to form two integers out of these 4 prime factors. And we're going to put 17 and 11 in 2 separate groups because these are the 2 largest prime factors. And when they're multiplied with something else, we want to make sure that the numbers are under 2 digits. So if we take 17 and multiply that by 5, which is the smallest prime factor, that gives us 85. And if we take 11 and multiply by 7, that gives us 77. So these are the 2 positive integers where their product equals to 6,545, and they're both 2-digit numbers. Okay. So this concludes our lesson today for greatest common factor. In our next lesson, we'll be introducing a new concept called least common multiples, and we'll be working on some problems where we use both least common multiples and GCFs. We'll see you next time.